Yeah, I am sharing. Hi all, I am sharing my screen. So in today we will going to see the syllabus, okay, and the basic flow of the analog design, and also we will go to see the tool by a simple circuit. Okay, so yeah, let me go through the syllabus that what we will cover in this whole period of training. Okay, I am sharing my screen. Okay, so are you able to see? Is it visual?
Yes, sir.
Oh, okay. Okay, so the first module of this training, we are going to see the Linux environment and the Cadence tool. Okay, so if we are working on the Cadence tool, okay, we have to go through the Linux environment. There, we want to make the directory, we want to delete the directory, we want to copy or move anything. Okay, for that basic thing, we should know the Linux command. Okay, so that we will see in our first module. Okay, that how we are going to copy the file and the file and how we are going to delete the file. Okay, then in the second module we will going to cover the fabrication, so fabrication of the CMOS, okay, and the FinFET. What are the different steps for the fabricating CMOS and the FinFET? Okay, so we will see these two in very short. Okay, because this is not that much usable in analog design. Okay, our main thing start from here, the semiconductor and MOSFET fundamental. So in this module we are going to see some basic semiconductor physics. Okay, that how we are doing the doping, what is the intrinsic and semiconductor. Okay, what is the p and n type semiconductor. So this whole thing we are going to cover in this basic semiconductor physics. Then we will see the PN junction concept. Okay, how the energy, okay, band gap energy is going to change across the PN junction. So I think you all have already covered this in your BTech. Okay, during your BTech you have seen how the energy profile across the junction of the PN junction diode or across the MOS, the metal oxide semiconductor. Okay, so this is the same basic things from electronic device of the BTech. Okay, so we will see the same CMOS technology overview, then MOSFET operation region. So there are three region, as you know, the linear cutoff and the saturation region. So this we are going to see as a MOSFET operating. Okay, then threshold voltage, how our threshold voltage is changing. Okay, what are the different factors that will change our threshold voltage of the MOSFET at device level. Then we will see the body effect that we call the backgate effect also. Okay, how our body effect is going to change the threshold voltage and all, we will see. Okay, and how this body effect is happening in the MOSFET. Then we will see the channel length modulation. Okay, and short channel effect, a small signal MOS model we will see, and GMR not and GMB concept. This GMB is because of the body effect only. Okay, this GMB, the GM is the transconductance. Okay, so this is the basic. If you have did BTech, then you have covered all these things. Okay, now we will, after that we will study the uh, MOS MOS modeling. Okay, MOS device modeling, semi like this MOSFET device, how it is going to work. Okay, at the device level. So we will see what are the region of operation we have already seen. We will see in the tool also. Okay, Then we will see how the current is going to vary with the length of the device, the width of the device. This called the device characterization. So we will take one device and we will do characterization of that device. Okay, and we will see how our drain current is varying with is like with WL. Okay, how GM is varying with how the GM ID relationship is there. Okay, so all these things we will do at the device level. Then we will move to the amplifier, the single stage amplifier. Okay, there we will see the common source amplifier. Okay, source degeneration amplifier, right? And we will see the basically we will see the fourth thing here. First, what is the gain of the amplifier? Okay, then we will see what is the output impedance of the amplifier, what is the overall transconductance of the amplifier, and then what is the location of pole and zero for a given amplifier. So all these four thing is important. If we know all these four thing, we will going to build a good amplifier with good gain, good phase margin. Okay, so that we will see in the single stage amplifier. Then we will see the cascode amplifier. Okay, so that we will see after that. Okay, and by after covering this, we will focus on the current mirror. So there are different type of current mirror. Okay, the first one is basic current mirror. So we will see the advantage and disadvantage of the basic current mirror. Okay, then we will going to make this more robust. Okay, we will going to make this basic current mirror more robust. Okay, so we don't want our output current to change. Okay, for that we will going to the cascode current mirror. Okay, the Wilson current mirror, Wilder current mirror. Okay, one by one we will cover that. Then we will in current mirror only we will see the minimum drain voltage that we needed to drive all the MOS device into the saturation region, right? Then we will move to the differential amplifier. So basic differential amplifier. Okay, and we will see what is the gain. Okay, the single lead gain and the differential gain also, how the output impedance. Okay, how the gain is impacting, how we are going to design this differential amplifier. Okay, whether we will keep this differential amplifier input pair in the subthreshold region or not, when we have to keep in subthreshold region and when we have to keep in the saturation region. Okay, that thing we will going to see. Then we will see the 5T OTA. Okay, so this is very important. I think here one thing is missing, the RC circuit. Okay, we will first going to cover the RC circuit. That is very important, because if you will see in the analog everywhere the parasitic resistor and the parasitic capacitor. So before starting this MOSFET, we should know how our how our device will going to react. Okay, so everywhere we will find the RC. So each node having one capacitor and each metal having the resistor. So that is very important to learn the RC circuit first. Okay, so yeah, we will then where were we? Okay, differential. Then we will see the 5T OTA. So for 5T OTA, we will study what is the gain again, the gain, overall transconductance, the output impedance, right? The pole and the zero. And then we will move to the two-stage OTA. In two-stage OTA, we will see the compensation technique. So there is various compensation technique is there. Suppose that Miller compensation, that is the very basic. Then Ahuja compensation, lead lag compensation. Okay, so we will see what is the scenario when we are going to use this type of compensation. Okay, and for each circuit we will also study the noise. Okay, how what is the thermal noise, is the noise due to the resistor and the noise due to the MOSFET. So they are basically the MOSFET device have two type of noise, the thermal noise and the 1 by f noise. Okay, that we call the flicker noise. So this whole thing is here, and we will see the stability. Okay, the by doing frequency analysis only we will see the stability of the device, right? So this all thing is here. Operational amplifier like single stage op amp, two stage op amp, folded cascode op amp, telescopic op amp. Okay, the gain boosting op amp. We call this GM boosting also op amp. Compensation technique. I have already told like the three compensation like Miller compensation, Ahuja compensation. Okay, then lead lag compensation. All okay. Then we will see what the phase margin we should have. So for analog, we wanted to keep the phase margin greater than equal to 60 degree. But the many circuit that will work at 50 degree also phase margin. So if our phase margin is less, we will do the transient simulation to see whether it is ringing or not in the transient simulation. So if our circuit is ringing in the transient simulation, then we will improve the phase margin. That means the stability of the device. Okay, we will see the slew rate. We will cover CMRR and the PSRR, power supply rejection ratio and the common mode rejection ratio. Okay. Then after this, once we have the knowledge of all these things, then we will going to start a project like a small project like band gap reference concept. Okay. So this is a one of the important circuit, okay, in the power management integrated circuit. So you know all the whole our chip or means what are the like if I have kept the ADC, okay, if I have kept the different block on my chip, so for all those block we will provide the supply, and that supply should don't have any ringing. So to avoid that, we placed the power management block there. So in power management block we have the BGR. Okay, the output of the BGR will go to the LDO, and then output of the LDO will act as a supply to all this a small block that will be on the chip, so that we will give a uh, smooth voltage or smooth power supply to the all the block that is on the chip. So for that we need the power management integrated circuit block, and the starting of that is the band gap reference concept. Okay, so once we will understand what is the band gap, how it is work, okay, what are the type of the band gap, okay, like there is two type, the current mode and the voltage mode band gap. Okay, then we will see for this also we will see the stability, PSRR, okay, everything that uh, like CTET and the PTET current, okay, and what are the startup failure in the circuit, right? So as you know, the stable state of this band gap having the two, either it will be work when it is work normal or it will be off. Okay, so this two state is a stable state for that band gap. So when we start the band gap, either it will be on the normal stage or it will never start. So never start stage is also the stable state for that band gap, right? So to make our band gap working good, we use the startup circuit, right? So this startup circuit is also important. We will see whether our startup circuit is working or not. Okay, when we will run the MC simulation, MC is the Monte Carlo simulation, then whether this startup circuit is creating any issue or not. Okay, so this thing we will going to cover in the band gap reference concept. Then we will, then our second project will be the LDO. So again, the output voltage of the this BGR will act as a reference voltage for the LDO. So we will see the LDO architecture. Okay, we will study how the pass transistor is controlling the load current, right? Then we will see the error amplifier. The basically the error amplifier that we use depending upon the demand. So either we can use the two-stage folded cascode, okay, amplifier, or we can use the balance load OTA depending upon the demand. Then we will see the stability concept, frequency compensation, load regulation, line regulation, transient response, and the PSRR concept. So this thing, and here in load line there is two. One is a static load line regulation, and other is dynamic load and the line regulation. We will see both, right? Then for this PLL, we will go through the concept, the theory, and we have the circuit. We will explain the circuit, but since this is the very big block, we will not going to design from the scratch. Okay, we will have the PLL. We will go to the different block of the sub block of the PLL. We will not design by ourselves. If you guys are interested, you can design this PLL, and we can support you while designing, because this is the big block and we cannot cover in this 6 month of period of the training, right? So this PLL we will provide you basic and this circuit, and we will explain the circuit to you. So in PLL there is four sub block. Okay, the one is the phase detector, and second one is the loop filter, third block is the VCO, and fourth block is the frequency divider. So this total four block will come in the PLL, four sub block. So we will see there PLL fundamental, feedback control basic, phase detector, phase frequency detector, what is the charge pump, loop filter, okay, voltage control oscillator, frequency divider, what is there is different frequency acquisition range for the PLL. So first we tell like what is the lock-in range, okay, what is the capture range, okay, this all the range we will going to see for the PLL. Then we will see the jitter and the phase noise. So how jitter and phase noise is affecting our output frequency of the PLL. Okay, we want always, like if I am giving 10 gig means I want 10 gig. I don't want any duty cycle variation there. Okay, we want the ideal clock like 50% duty cycle, but in practical scenario we will not get the 50% duty cycle clock. We always have some jitter. So there is the various type of jitter like deterministic jitter, okay, and a jitter due to the noise of the device, okay. So we, as an analog designer, if we will work on the high speed device, we will always going to reduce the jitter. This, if we will see the eye diagram, the width of the crossing will show the jitter. So we always want to maximum eye opening of the eye diagram, so that jitter will be less and our clock will be good, okay. Now after that we will see the ADC. Again, in ADC we will not going to cover the SAR ADC and pipeline ADC, okay. We will cover only the basic ADC like flash ADC we will cover, okay. And we will see the DAC also. So there is different statics and the dynamic parameter for this ADC, okay. We will going to cover all like INL, DNL, and this INL, one thing, DNL is what is the INL, DNL of the ADC, and then what is the this uh, what called N, wait, INL, DNL, and this because of the INL, DNL, we there is many dynamic parameters also there. We will going to see this like ENOB, what is the ENOB, ENOB, okay. How it is going to affect our ADC, right? So this thing we will see, and you have already seen in the your BTech this sampling theorem and the quantization and comparator fundamental. This I think you have already seen what is the quantization in the communication system and the sampling theorem, right? And because of this quantization we will get an error that is called the quantization error. This quantization error is important here, that will only provide the this the ENOB, okay, the effective number of bit and all, okay. Okay, then we will see some memory concept design like some digital thing like memory fundamental, SRAM 60, SRAM read write mechanism, pre-charge circuit, sense amplifier, decoder. Okay, this all the digital thing. Okay, the bit cell stability, SRAM noise margin, DRAM basics, and ROM fundamental. And we will going to design this all thing on the Cadence Virtuoso tool. Okay, and this three node we will use 5, 12, 16, and the TSMC node, and then GPDK node 45 or 90 degree, whatever will available. Okay, this is the syllabus. Okay, that we will cover. So if I will divide this syllabus depending upon the fresher, so mostly the RC circuit. Okay, RC circuit, it carry the 40 percentage weightage, because if you will sit in the interview and interviewer will ask mostly question from the RC circuit. Okay, then they will ask from the basic of the MOSFET, then single stage amplifier, like what is the output impedance, what is the location of the pole zero, what is the gain, that they will ask. Okay, then they will ask the 5T OTA, and similarly they will move to the two stage OTA. So this 4 5 thing is very very important. They will cover 100% of your interview. This only four topic: the RC circuit, basic MOSFET device, single stage amplifier, 5T OTA, and the two stage OTA. Okay, these five topic cover your 100% of the interview. Okay, interviewer will, if you will tell that I have worked on the band gap preference concept, then only they will ask the question from band gap preference. Okay, because for fresher and even for experience also, they will check the basic knowledge, that do you have the basic knowledge or not. So for that, this five topic is very very important. Okay, so if anyone having any doubt, we can see here regarding the syllabus.
Uh, Hello, sir. I have a question.
Mm-hmm.
Sir, my name is Abhijit. So, sir, currently I am working in a research project in the analog design only. Okay. So, as a part,
Mm-hmm.
as in a research point of view, we study various research paper, see their output result, and after going through that, we make our own specification and design a circuit. But like in industry, how the approach is done means if I means the specification is given, or we have to take the make our own specification or design, means how the design approach is done in the industry level. So that's my question.
Okay, so in industry, if you are working on the project, imported project means porting project, not imported, porting project. So if I am working on some high speed design, high speed serializer and deserializer, and if it is porting from some technology node to some other technology node, suppose if it is porting from 7 nanometer to 5 nanometer, then 4 nanometer, then already a spec was there. Okay, and then we have to only simulate and check whether we are meeting our spec or not. If we are not meeting our spec, we will tune the circuit to meet the spec. Spec is a specification. Okay, but suppose if we are going to design anything from scratch. Okay, if I want to design 5T OTA from scratch, so depending upon the requirement of the customer, how much gain they want, how much phase margin they want, what is the range of the frequency, what is the range of the temperature they want. Okay, and what is the supply they want. Depending upon that, we will design the circuit to meet the spec, like gain, range of the supply, right? Then range of the temperature, whether my design will be satisfy that range or not. Okay, then then the stability, depend upon the delay of the circuit. Okay, everything we will decide depending upon the requirement of the customer for the scratch project. Okay, but if some project is ported, the specification is already there. Yeah, is it okay?
Okay, sir. Okay, sir. So another thing, will you will be covering the theoretical aspect in this also, in this course also, right?
Yeah, theory and tool both.
Okay.
We will
Okay, sir.
cover
Thank
the
you.
first theory, and then we will see the circuit on the tool.
And sir, how do you find the approach? Like, for example, I am saying that if some new design comes to you, like if our OTA means you don't know about the OTA, but some client have given you to design the OTA, means from scratch. How do you define that project? Means how the circuit you find that circuit, that this circuit is suitable for that particular project. How do you define those things? Means in industry.
Yeah, so if a customer is asking like I want this gain, okay. So suppose they are asking I want the more gain. So this 5T OTA will not give that much gain, right? So for that we have to go through the folded cascode OTA. Okay. So but there is always some advantage and disadvantage of the any circuit. So depending upon what they want, okay, how much our circuit be robust, okay, robust also we have to make our circuit so that it will work at 0 degree also, it will work at 50 degree also, it will work at the 125 degree also, right? Even for some case it will, for maximum case it will work from -70 to 1, or -40 to 1, -70 to 125 or something like that, depending upon the range of the temperature. So whether first if suppose if some customer will tell that I want the 60 dB gain, okay, and I want the phase margin greater than 60 degree, okay, I want the slew rate 5 volt per microsecond. So depending upon that, I should have the enough knowledge that which circuit will be best fitted for this. Okay, suppose you are I need the gain of 80 dB, right? And if I am making 5T OTA, it will not going to give you 80 dB, right? For getting that we have to use different this OTA, like folded cascode OTA with the two stage. So first stage will give some gain and second stage will give some gain, and multiplying this gain we will make this more, right?
Okay, sir.
So
Got it, sir.
depending upon that only we will design. And first before designing we should have the knowledge of the circuit, that if I am changing any device, how the circuit will going to work, going to react, okay.
Okay,
And
sir.
we will see some paper, okay, before starting some IEEE paper, good paper, okay, and then there we will have idea if we are junior, okay.
Okay, sir. Got it, sir.
Hmm. Okay.
Hello, sir. Sir, my question is like,
Hmm.
sir, per month, how many modules we are going to cover?
Okay, this whole syllabus is for 6 months, okay, and the
Yes.
class will be on weekend, Saturday, Sunday.
Okay. And sir, I just want to know, like, per month, like, suppose in first month, like, we are going to cover 2 modules, 3 modules, like that. And sir, one other question is there, like, after covering each module, we are going to do some projects, or like at the end, we are going to do some project.
After covering, it will be theory plus practical both.
Okay, sir.
But parallelly, it will run because if we do it in last, many of the guys will forget the answer by many things.
Ah, yes, sir.
Then it will be difficult for everyone to do.
Okay, sir.
Okay. Sir, you can use the tool
Sir,
once.
No, okay.
sir,
First,
I also
uh
have a doubt. Do you
Ah,
guys also provide placement services also?
yes, placement support is there. Placement job
Sir,
assistance is there. So I think I don't remember your name.
sir,
I
I
think
have
I have talked to whomever I've talked. I have provided that. I've told that job assistance with certificate of completion is available in the course actually.
I have never spoken to you. I have just joined the link for the first time.
Oh, okay. Might be, I
Yes,
think
sir.
you joined from the group directly.
Yes, yes.
Okay. You can ping
Sir,
me if you have any queries related to anything. You can ping me.
okay, sir.
The chat number in the phone number that which I have provided, the Bharat IT. You can ping
Yes,
me
sir.
that one. I will help you out. And
Okay,
job
sir.
assistance and certificate of completion is provided with this course.
Okay. And what is the average package, sir?
See, the average packet depends. If it's a service-based company, then 5-6 lakh, six maximum if you get. In
Okay,
general, it is 4.5 to 5 because Wipro or HCL they provides 4.5 to 5 maximum. If it is a product-based company, then suppose It depends. So which kind of product company is giving? If Intel is providing, they generally provides 12, 13. I'm talking about BTech this one. If it is MTech, little bit of higher package will be there. Okay, so
Actually,
if it is Synopsys, yeah, tell me.
yes. Actually, I'm pursuing PhD right now.
See, there is no salary package in generally specific for PhD. It
Yes, sir.
depends. In generally, every PhD candidate is considered as a fresher in the industry only. Okay, it depends upon the company to company. Just like see, if you see Qualcomm's job description, they will
Yes, sir.
provide. If you have PhD experience, then minimum, I think 2 years of experience is needed, example wise. With
Okay.
PhD, 2 years of experience. With masters, 5 years of experience. With
Okay.
if you have a BTech, then you need 8 years of experience. With 8 years plus BTech. If you have BTech, then you need 8 years. So this kind of variation will be there. So
Yes, sir.
you call yourself as a, you can tell them that you are a PhD student, but it depends upon the company how they generally treat you. Because generally they will treat you as a fresher only.
Yes, sir.
Point wise, see, PhD is also a experience kind of thing, a research point of view. But
Yes, sir.
company in generally don't
Consider that.
matter that one. So that is the
Yes,
issue
sir.
actually. Else everything is fine.
So, sir, your company have tie-ups with Qualcomm's and Intel also. Well, like
No, no,
you
no.
help us.
Any product company, no product company do tie up, right? Service
Okay.
company has tie up. Wipro we have tie up. We have HCL we have tie up. We
Okay.
modernized
Okay.
Tip Solution we have tie up. Sprintronics we have tie up. But product company don't do tie up. They yeah, we have contact with HR when they put the opportunities, they come to us. But if you ask me any official MOUs will they, no product company generally does that one.
Yes, sir. Yes, sir. But you will help us for that also. For
Can you repeat
Qualcomm and
again? Hello? Hello? Hello?
hello.
Yeah, I'm audible.
Yeah, yeah, you are audible, sir. So I was asking but you will help us with those interviews also for
Yeah,
Qualcomm and the basic.
if job opportunity is there, for sure we will be help you out. If there is no job opportunity for fresher from the product company, no one can help you out in that case.
Obviously, sir.
It's a
Correct.
stretch in the starting only. I am saying that one.
Yes,
See,
sir. Yes.
everything job assistance matter when market is open. Candidate is also performing well in the interview. If candidate don't perform, then how we can place a candidate?
Obviously, sir. Obviously.
Okay,
Yes, sir.
so that these two things matters for get a job assistance.
Yes,
Okay,
sir.
yes, sir. You can take over the tool. So you have Ultra Viewer, sir.
Sir, one last question.
Yeah, tell
Sir, I
me.
just want to know, like on 16th, like when we are going to join this program, on that day only we are getting the tool access, or like when?
Tool access is provided in the starting only. Because I told you, I think one guy asked me a question that when we will learn the product, I told that parallelly everything will be taken care. Theory and practical will be there. So, see, initial theory like CMOS basics when you are learning, right? What are
Yes.
operating condition of a CMOS? You have to know, you have to simulate it. Nah? Otherwise, what is the benefit? So, I think many things you have studied in your BTech, right? You might not have
Yes.
studied LDO and BGR, I understand, but CMOS operating conditions, triad
Yes.
region, or saturation region, cutoff region. So to know this one, whether your transistor is performing properly, what your with your parameters, you have to simulate. Na? Then only you will get those results.
And mostly, sir, we are working on cadence only, no?
Cadence is there, and see, 95% cadence you will work because cadence is the main thing is mostly used in analog background. If you want to use 5 nanometer, then you have to go for Synopsys custom compiler.
Okay, sir. Okay, sir.
So both we will be providing. So that is the reason. Let me speak with sir once, so sir can show you the tool. Hello, sir.
Hmm.
Sir, you
Yeah.
can you have
Can
ultra
we
viewer.
go
You
to
can
the flow, analog design flow?
yeah, you can continue. So you can continue. So if you
Okay.
have ultra viewer, you can take access to the tool once.
Okay. Okay.
So if you have, please get the ultra viewer once.
I think I have the cadence GPDK. I will show the how it is going to work. Okay. Hello.
So actually, I was thinking to show on TSMC. TSMC 16 or 12 nanometer global foundry. If you have access,
Okay,
you can
that.
access it from here.
No, no. I will have to see that. I have to check that. I can open the GPDK 45. That is, I have.
Okay, so can you guide me, sir, once so that I can help you out?
Regarding this
Hello.
tool. Hello.
Yeah, tool. Yeah, tool regarding tool. I am sharing the screen.
Okay. One second.
I am sharing the screen here. Let me present it now. Okay. Let me present it now. Just quick demonstration of the tool I will show and I will left out so sir can continue. Okay. Okay. Sir, so okay. So this is cadence tool. Okay. So this is cadence tool. Everyone, I think many are aware of the tool. Many are not aware. So please see, this is the cadence tool, cadence virtuoso. Studio IP 23.1 is the latest version of the cadence. 25 has also came, but 25 and 23 doesn't have any difference. So both are same. Okay. So any version updates are only there. So for the work purpose, we will be teaching on Global Foundries 12 nanometer, TSMC 16 nanometer, and UMC 28 nanometer in the class, and 5 nanometer will be also there. Apart from this one, we have other technology nodes also, TSMC 40, TSMC 65, SCL 180. We are actually making our own LDO. So we are using TSMC the SCL 180 for our fabrication purpose also. Apart from that one, we have other technology nodes like UMC 110 and 190. These are also there. Global Foundries 55 is also there, and UMC 40. So whichever candidates want to use, you will get access to all. You can use any one of them. But in class, teachings will happen only on 12 nanometer, 16 nanometer, 28 nanometer, and 5 nanometer. Because every point cannot be covered over the class over a period of time. Okay. Now, the thing is, this is the library manager. This is the cadence virtuoso. This is the, once again, this small guy is called the CIW window, command interface window. Everything you can play with here. You can open the library manager from here, everything. So this is the library manager. Okay. In this one, all the libraries are present. You can play, you can create library, you can make things, many of the things. Okay. Apart from this one, I can go. This is the schematic. So this is the schematic I have built in TSMC 40 for now. Okay, so in TSMC 40 nanometer, I have built it for now. Okay, so this is a example of an inverter simply. Okay, and after that one, we can create a small test bench. VDC as 1.8 volt and V pulse. I have given here as a connection. You can query it to see the parameters what I have used there, basic parameters. It is the output. And then we will take this to the simulation system, which is called ADE Explorer and ADE Assembler. This is the ADE Explorer one. Okay. Here, when we will come here, we will simulate and check what is the result here. Okay. So if I now try to simulate it once, click run, many things will come into picture. We will teach you in the class in detail how to operate, how to do everything will be taken care in the class, how to do, what is the error, why one error will come here now. See, one error will come. This kind of situation happens every time when you do any kind of designs. Okay, see, sim error came, right? Why this sim error came? This sim error came because, oh, one second. Let me remove these two, right? Don't need them. Okay, let me resimulate it again. It is visible to everyone? Hello? Is it visible to everyone? Screen?
Yes, sir.
Okay. See, again, sim error came. Why the sim error came? Okay, so simulation error came because it show a error found in Spectre. See, when you open this log graph, you will able to see what is the error. You will get to know error M0. M0 means, in our case, M0 is this transistor. This is the M0 guy. PMOS is the M0 here. Okay. You need to open this one and see what is the error now. So if the effective length is less than or equal to 0 because the value of one or more parameter related to effective length is less than and equal to 0. So parameter error is there. So we have to fix this parameter to run the simulation. Okay. So sir is more experienced in this one. I will put it over I will transfer it over sir. So sir can help you out in this one. Sir, can you check this one error?
Yes, if actually the screen is not visible properly. I am not able to read. What is this?
The error is
Effective
flagging here
length.
is
Uh,
the effective length is less than or equal to 0 because the value of one or more parameter related to the effective length is less than or equal to 0. Check and update the length related to instance and model parameter.
okay. This is coming for M naught.
M not this
Yeah.
PMOS.
Okay, we can see the M naught, the effective length, what is there.
Okay, so this is the
You that.
uh,
Uh, what is the length given here?
length is
Effective
40
length.
nanometer.
Uh-huh. Okay. Can you increase this?
Yeah, I can. How much shall I put? 100?
Make 100, 500. It is okay.
100 I have given. Okay,
100
100
nano.
nanometer. Yeah, 100
M is
nanometer.
coming. Okay.
M is the
Can you
capital
remove
one.
M? Can you remove M?
Yeah, I have
Give
removed.
100 and only. Here
Here also
also.
I will remove the M.
M
So
is
finger width is for 140 nanometer and width is only 140 nanometer. Number of finger and multiplier are 1.
Okay. Okay.
Okay. Now
Uh,
the
this
NCH
one.
one is this guy
You
is actually the same 40 nanometer. Shall I make it 100 nanometer?
make this 100.
100 nanometer. M is automatically coming.
It's okay.
140
140.0. 140.
N.
You make this 140.
Yeah, done.
N. N.
Done.
Okay. Okay.
Okay.
Uh,
Let me save it. Let me go here and play it. I have kept it in transient analysis in 200N. Okay. 300N.
hmm, okay. Again,
See, it
error
is
is.
giving the same. That error is coming.
Yeah. What is the error? Again, same.
Same error with the M0 only.
Okay. Actually, it is not visible clearly for me. The effective length is less. Okay, we will check this later.
Okay.
Mhm.
So this the way we generally find out the errors actually, how to figure out the error, what are the errors actually. So we get to know what are the exact errors so that we can figure out the things actually. So to understand the whole scenario. Okay. See, to simulate, sir, you can continue. So to simulate anything, we can do many steps. We can do it. So we can make the steps multiply. Okay. So let's sir complete the thing. I will get back to you again on this one with a simulation result. Okay. Sir, you can take care.
Okay.
Okay,
Yeah.
sir.
Mhm. Is my screen visible? Okay. Is my screen visible? Are you able to see? Oh, okay. So, yeah, we will see. 1 second. Um, Wait. Okay. Are you able to see this flow chart? So first, when we will going to start designing anything, any project, first we need the design specification. Okay. So this design specification is provided by the customer, that what they want from our circuit. Okay. So once we will get the design specification, then we will go to the virtuoso cadence, okay, in the schematic, and we will design the schematic. Okay, we will design the circuit. So once we will design the circuit, then we will convert the circuit into the symbol, and then we will create the test bench, right? And in that test bench we will provide the voltage source and the stimuli whatever the needed, and then we will do the simulation, and that simulation we call the pre-layout simulation. So once the simulation result will come, okay, we will check whether we are meeting the spec or not, worst case spec. Okay, if suppose anyone is telling that we have to make the 5T OT of 60 dB gain, so we will simulate that and we will see whether we are getting 60 dB gain or not. Suppose if we are getting less than 60 dB for the worst corner, then again we will go to the schematic editor and we will tune our circuit. Okay, and then again we will do the simulation. If now at this time if I am getting the worst gain is 65 dB, then okay, my schematic is correct, and now I can give this schematic to the layout design engineer. Now what the layout design engineer will do, they will design the layout for this 5T OTA. Okay, and after designing the layout, they will do the DRC and LVS, and then they will do the parasitic extraction. Then we will take that extracted file and we will keep into the config of the that test bench, and we will do the simulation. That simulation we call the post layout simulation. So if we are meeting the spec, this is okay, and if we are not meeting the spec, then again here if we are not meeting the spec, suppose the phase margin is greater than 60 degree and we are getting 45 degree, so there is two issue: either our schematic is not correct or the layout is not correct. Since in a schematic we are getting suppose 65 degree phase margin, so there will not the 10-20 degree difference in the post layout and the pre layout simulation, then this means the layout is not correct. So again we will convey to the layout engineer that we have to minimize the some parasitic cap. Okay, or we have to do something to improve the layout design. So once again if they will do any modification in the layout, again they will do the DRC LVS. LVS is the layout versus schematic, DRC is the design rule check. Then again they will do the parasitic extraction, and we will get the extracted file and we will run the post layout simulation. This will go in the iterative manner if we are not meeting our spec. Once we will meeting our spec, then we will generate the GDS2 file and we will send to the foundry to for fabrication. So this is the overall flow of the analog design. Okay, in this way we will work in the industry. Okay. So anyone having any doubt in this, then you can ask this flow.
Sir, someone has asked question in the chat. Just look into it once.
Okay. what will be the book we are going to follow throughout the, yeah, the, like for analog design engineer, the Rajavi. Okay, Rajavi is the Bible for us, so we have to follow that. Okay, analog IC design by the Rajavi, Bejad Rajavi. Yeah, any other.
Then you can show them the simulations at their end. Hello?
Hello.
Yeah, you can show them the simulations at their end. Actually, I am facing some internet issue on my system.
Simulation from my end.
Yeah, from your cadence, you can show them. Okay.
Okay, okay. Yeah, I am opening that cadence. Let me
Yeah.
open.
Actually, I am facing some connectivity issue at my end.
Let me open. Okay, so I am sharing my screen. Yeah. So if you will see, this is the cadence environment. Okay. And what I have opened, this is analog design.
So your screen is not visible.
This environment. Okay.
Oh, now,
Okay.
now it is visible.
Now it is visible. Okay. So this is the folded cascode that I have designed, that I am showing here. But see, so I think it is working very slow. So this is CIW window. Okay. Uh, as the sir explained, this is called the library manager. So everything that we will keep, okay, every technology node and our project, everything will be come under the library. Okay, then each library have the some cell. Okay, each library will have some cell. So this is the cell present here. Okay, and this is, in this cell, either we have the schematic or the test bench. So schematic is simply, if suppose if I am making any inverter, okay, let me open this. So suppose this is the inverter. So if I am not providing any this voltage here, then it will be a schematic. Okay, and for that schematic we will do the symbol, and that symbol we will use in the test bench, and we will provide the supply. Okay, that is the correct way of doing, right? So suppose this is my test bench. Okay, I just kept the one PMOS or one NMOS, and I am running the simulation. Okay, so if you see, this is the GPDK 90 nanometer technology. Okay, this is the PMOS. Okay, if for Q we will Q this. Okay, if we will press on device and Q, it will show. the multiplier, okay, length, width, finger threshold, everything. Similarly, for NMOS, we will click on the NMOS and we will see what is the length, width of the device. Okay, just click on that and then press Q from your keyboard. Okay, now I have kept 1 micrometer for the NMOS and the 1.5 micrometer for the PMOS. Right. Can anyone tell what is the relationship between the mobility of the PMOS and NMOS?
Sir, mobility of NMOS is greater than PMOS because
How
mass
much?
of electron is
How much greater?
it's around 2.5 times, 2.5 or 3 times more than NMOS, PMOS. Sorry. Like,
Even not, is it 2.5?
sir, actually, I'm not to the correct figure, but the mobility of NMOS is more in comparison to PMOS because mass of electron is less than mass of holes. That's why mobility of electrons are less.
Yeah, for larger channel, for long channel MOSFET, it will be twice. The mobility of NMOS will be twice the mobility of PMOS. If we will decrease the technology node, suppose that if we are working on the 5 nanometer, then for both we will keep the same length. Okay. So for when we will do the characterization for the inverter, we will see whether the output and the input is crossing the midpoint. And for what is the W by L ratio of PMOS to the W by L ratio of NMOS, we are getting crossing of the output and input at 0.5 of VDD. That will be the W by L, and that will be the ratio between the W by L of PMOS and the W by L of the NMOS. Okay. If you see in the lower technology node, the width of both, okay, PMOS and NMOS, we keep the same. And here 180 degree I have kept 1.5 time. If you see for the TSMC 28 nanometer, there you will keep 1.2 time. The width of the PMOS will be 1.2 time the width of the NMOS. Then we will get the good result. Okay. Okay. So this is my test bench. Now I am going to launch the ADXL. Okay, either, so see here is different thing. If you see ADEL, ADEXL, ADGXL, okay, this is layout GXL schematical. Okay, see this is the different version. Either we can open do the simulation in ADEL or ADEXL or ADE Explorer, ADE Assembler. Every the simulation, the way of doing simulation is same for everything. Okay, but only improved version. Suppose if I am working on ADEL, so this is the basic. If I, sorry, some, can you mute yourself? If if I will work on AD assembler, that will be the more good, more user friendly compared to the ADXL, ADEL. Okay, that is the update, only update in the different this, but all are the same. The way of doing simulation is same for every. Okay, so I am launching the ADEL. Okay.
In the newer version, ADEL has been replaced with ADE Explorer and ADE
Yes.
Excel has been with ADE Assembler.
Yeah. So yes, the ADE Explorer and ADE Assembler will be there in the new version of the Cadence.
Yeah, first let complete, sir, complete. So I will show you the simulation of inverter in UMC 28 nanometer. Okay, so it is running now. Some issue came, so let's, sir, you complete, then I will show it to them.
Okay. Actually, this tool is very slow. What is this? Okay, this is the inverter only. It is open here. Okay. So what we will do, we will this is the ADEL. Okay. If we will click on ADEL, this will open. Then what we will do, we will go to the analysis. Okay, from choose, here we can choose the different type of analysis like tangent, DC, AC, noise, P noise, XF. The XF we do for the PSRR. Okay, sense, DC match. Okay, STB for X stability of the device, PZ for pole zero analysis. Okay, the P noise. Okay, PSS, all these things we will go, all type of, for hit races we can find ST simulation. Okay, so this is the where we can choose the analysis. So since this is the inverter, we will going to do the tangent analysis for this. So we will select on tangent, then we will give the stop time. Okay, up to what time we are going to run the simulation. Now here is the different type of accuracy, the conservative, moderate, and the liberal. So once we will do liberal means the accuracy will be very less, and then moderate having the more accuracy, and conservative having the top accuracy. Okay, we generally keep in the moderate. Okay, but in project if you see we will keep in the conservative to get more realistic, okay, result. Then we will click on the apply and okay, right. Now what we will do, we will click on this and we will run the simulation. Okay, okay, let me add here input and the output. So what we will do, we will go output. Okay, to be saved or to be plotted, anything you can do, select on the schematic. So here we will select the output and the input. Okay, and then we will escape from your keyboard. Okay, escape. Okay, let me again find where it went. Okay, this is, so here it came. Okay, the input and the output. Now we will run. Okay, so this simulation is completed and we are seeing the output, the input and the output. From this, on clicking on this, we will separate this input and the output. And if we want to drag out input up and output down, we will keep this down and it will come. Okay, I want this output upside. Wait, this is slow, the tool itself. Okay, I want this out input upside and output down. So input is up and the output is down. Okay, so this way we will see the result of the inverter. So what the inverter do, on clicking V from your keyboard we will get the vertical marker. On clicking H from your keyboard we will get the horizontal marker. So since this is the inverter, so input, if input will be 1, then output will be 0. You can see the input is 1, green one is input and the red one is output. So if input is 1, output is 0. Okay, and if input is 0, then the output is 1. And what other thing also we will going to see, we will going to see the delay. What is the delay? So when we are giving the 1, what is the time it is taking to take the 0? So see here, approximately if you point this to the middle. Okay, since this is the 2 volt, we will keep to the 1 volt. Okay, from here we can change the value, right. Okay, this whole thing we will going to learn slowly. Okay, so you can see the delay between input and the output is 4.38 nanosecond. Okay, so when the input is making transition from 0 to 1, after 4 nanosecond we are getting the transition of the output from 1 to 0. You can see, if you want to zoom, you just press your right button from your mouse and you can zoom. So you can see the input is going from 0 to 1 and the output is coming from 1 to 0 here. Okay, so this is the simulation result. Okay, of the inverter. Yeah, yes sir, you can continue.
Yeah. So I will be resharing my screen again. Okay. So sir has shown the inverter in a generic GPDK, right? Just to show the how it happens. Okay. Actually, I am from layout background, so sir is more knowledgeable in circuit. Okay. So I am less knowledgeable in circuit. I am from layout background. The layout comes after the circuit design. Okay. When you plan this whole thing in a layer by level, transistor level. Okay. So I have created a basic inverter circuit in a UMC 28 nanometer. Okay. So if I click, it is UMC 28 nanometer. Just please check. Okay. Parameters are already been set. This all thing you guys will be doing on your hand. Why? Like, see, suppose this is a V pulse. Okay. We are putting a V pulse in the input and query. Why we are putting these values? What are the necessity of those values? Sir will teach everything in detail in the class. The requirement. Okay. After this thing is done, simply click check save. It is done. launch ADE Explorer. Sir, they are shown ADEL, ADE Excel. So here it has changed to, these are the latest versions. And the reason it is ADE Explorer, ADE Assembler. So I am opening ADE Explorer. So already I have set up one test bench here. Okay, Mastro. Okay, 1 second, it is opening. Okay. So how I have done, I tell you. So here corners have been set. So some of the things have been set. Why? I tell you, in PVT corners, this have been set up. So if I turn on this cell, this temperature, this symbol, can you see this symbol, temperature symbol? If I click this one, you will get what are the things. You can run those simulations in different temperature. See, slow in -40, fast in 125. I have just said so to check the PVT corners. Okay. Sir has shown which is the generic transient simulation. This is the PVT corner simulations. Okay. Here, and then we have set everything to this one, 200 nanoseconds in moderate also I have set here. Okay, so corners and parameters is there. Analysis is transient. Across that one we will do. We can do Monte Carlo simulations. Those will come later. Sir will teach all those things separately. Okay. So output and input has been given for a plot. I will simply click this button. Once I click this button, it will start simulating in 3 phases. You saw that one: nominal, slow, fast. Okay, so 3 parameters it will start simulating. 1 second, it will come here and automatically you will able to see 3 parameters are simulating here. 2 corners and 1 nominal corner. So 3 parameters it will simulate. Where it is simulating actually. I hope it has already net listing finished. One second, I think it is getting simulated. Okay. I am there here. Let me split the stress. You can see for every, so nominal. Okay, so what we can do, we can put them. So this is the input, that is the output. I just put it in the top side. So nominal input, nominal output. Okay, so again, output of SS and input of SS. So let me put it here. Okay, so input of SS, output of SS. So again, input of fast. See, now you can see it. Input of nominal, blue color, output of nominal in yellow. Input of nominal in input of slow in sky, output of slow in red. Input of fast in magenta, output of fast in green. So these are the 3 parameters in in nominal, -40 degrees slow and 125 degree in fast. Okay, so these all parameters we have simulated to check what are the condition or the functions of the simulations happening and our transistor how it is functioning or those temperature. This is how we simulate each and every step. Okay, this is the whole simulations you will be taking care. You will do Monte Carlo. Many things will come into picture in a later stage. Okay. If you have any queries, please ask me out so that we can help you on those topics. Hello? Hello? Anyone have any query? Hello?
Yeah, you
Any
are
queries
audible.
for anyone? No one has any queries? Hello? Hello, guys? Anyone? Any queries and sort of things? Okay, no one has any queries. Sir, you have to explain something? Hello, sir?
No, I think that is as we planned, right? So flow
Okay.
chart
One
and
more thing. Let me show them one thing that how a operational amplifier exactly looks like when we generally simulate it. 1 second. What happened to this guy? 1 second. Yeah. Now let me show it to them once. How a operational amplifier somehow looks like when we design it. Okay. So this is a circuit of a band gap reference. It is in SCL 180 nanometer. This guy. It is a example of a band gap reference. Okay. And this is the operational amplifier. Let's not touch the band gap reference at this moment. We will come to those band gap reference later. Just let me show you quickly operational amplifier here in test bench of Mastro. Okay. Let me show it to you quickly. Okay, see, this is the actual operational amplifier. Exactly, it should looks like this in a circuit level. Okay, schematic level. It is a two-stage. It is a two-stage operational amplifier. Okay, two-stage operational amplifier that has been implemented here. Okay, then we have created the test bench for them. Separate test benches have been created. Okay, now if the test benches have been created, I can open the Mastro. Mastro means the saved analysis. Okay, I will just click on this one. I will open it. See, many things have been taken care for similar XFF, CMRR, PSRR, loop gain, DB20, gain margin frequency, phase margin frequency, phase. Many things we have taken for simulations. If I click this one now as a simulations, let me check once. I think everything is set up properly. I think I click on this one. It will take a little bit of time. I think so, and it will give excellent results of the operational amplifier. Just have a look of that one, so you will get to know how the design happens and how it looks when we just simulate it properly. Just I think 1 or 2 minutes it will take time to get simulated. Till that one, anyone have any questions related to any topics and sort of things related to any job assistance, any query related to a topics, anything you guys can ask. We will be happy to help. Hello. So batch will be starting from next week, which is 16th of May. Okay, so we will be delivering all points of things over the group. Interested candidate contact me, so I will be helping out them for the further processes. Wait, it is simulating once. If I click here now, still I can see some graphs are there. Let it get simulated first. See, when it will get simulated, more informations will come into picture. But like CMRR, PSRR, many things will, whatever the simulations we have set up, everything will come. See, this is the transient response of the output of the operational amplifier. This is the output coming, this is the noise response coming, AC response, DC response, everything is there. See, step by step it is coming, step by step it is coming. See, this is the everything when we do design in industry, we do this kind of design, we show it to the clients or the manager or the team in this way actually, so that they can understand the whole hierarchy. Okay, this is the normal way to show to them. I think a little bit of more have got simulated. Let me reopen again, but everyone can see it properly. Okay, see, it is simulating in a proper way now. Okay, so this is how a operational amplifier simulations looks like. This is a basic two-stage operational amplifier, not a very expensive one. Okay, so don't worry for that one. So these are the simulation results are coming out. This is all about the things we are going to teach over the next couple of months. Excuse me. So I think everything is clear to everyone. So you guys, we can now go for a Q&A round session. So if questions are there, please ask us. Any questions?
Sir, can I ask question?
Yeah, they tell me.
Sir, basically, we will make a two-stage OTA. Sorry, we will start from the means how which block we will simulate the in schematic form. How much cost?
Sir, can you explain it? If you see in the syllabus, we have
Yeah.
taken operational amplifier, the different types of architecture of operational amplifier, two-stage folded cascade, OTA, everything we will be taking care. What are the architectures? Everything we will taken care. Okay. After that one, we will be using that operational amplifier to build a band gap reference. We can use that
So
operational amplifier to build a
which
ADC.
sir,
Tell me.
which OTA we will design then?
That sir will be able to answer better from me.
Okay.
Yeah,
Sir,
Then
can you repeat?
hello, sir. You can answer it.
Can you repeat?
Repeat the question, please.
sir, which OTA we will design?
Okay, so first we will start with the 5T OTA, 5 transistor operational transconductance amplifier. Okay, then we will design the 2 stage OTA. Okay, by using that 5T OTA and second common source stage and with Miller compensation, we will design 2 stage OTA. Then we will design the folded cascade OTA. Okay, this three is important. If time will be there, we will design the balanced load OTA and telescopic okay OTA. And for each and every circuit, we will going to see the stability analysis, the DC analysis, DC operating point analysis of the each device, as well as the frequency analysis. Okay, and the noise. These four are important.
And in current mirror, which we will design?
In current mirror, we will start with the basic current mirror. Okay, then to so what is the disadvantage of the basic current mirror? How we can overcome for to that disadvantage? So for that, we will going to design after basic the cascade current mirror. Okay, then the high voltage swing current mirror. Okay, then the wilder current mirror, like that only. We will going to one step one. The what is the disadvantage of this circuit? Then how we can make this better? So to make anything better in that circuit, we have to design other circuit, right? To minimize that disadvantage. Okay.
Okay.
So for that only, we will go step by step and we will design whatever the required necessity will be there. Okay.
And then for BGR and LDO, which OTA and OTA we will use then?
In BGR, we will we can use like 2 stage OTA or folded cascade OTA also,
Okay.
depending upon the requirement.
Okay. So which type of BGR we will design then?
We will design the voltage mode BGR, okay, and we will give the assignment to you to design the current mode BGR, okay.
Okay. Voltage mode, current mode. This the sub 1 volt or something like that?
Yeah, like in voltage mode VGR is the conventional VGR 1.2 volt VGR.
Okay.
Okay, there we will get the P-TED current and the C-TED current. Okay,
Okay.
and that current will going through the P-TED voltage and C-TED. Okay, and that it will go to the next branch and it will create your output. Okay, in
Yes.
current mode VGR, we will get the P-TED current, C-TED current, and that will sum and make the Z-TED current. That is zero absolute to temperature. And then we will feed through the register and we will get the output.
Okay.
Okay, so in BGR we will design the conventional BGR 1.2 volt and also the sub model BGR that you are telling on that below 1 volt. The below 1 volt BGR we call that BGR. Okay, current mode
Yeah.
like 0.8
Then
volt. Okay,
after this, will we design the PLL?
no, PLL we will not design. We will show you we will teach you the basic of the PLL. Then we will go through the already designed circuit. We will go through the circuit. Since designing this PLL will take time, even theory itself will take time, right? The PLL having the 5 block,
Yes.
no, the
Yes, sir.
PFD, then charge pump, then loop filter, VCO, and then frequency divider. So this is a big project, right? The PLL itself.
Okay.
So yeah, designing PLL will take time, and in this 6 month, right, we will not able to design the PLL. We will go through the basic and we will show you the design. We will explain the design. Okay, if you
And
are interested,
ADC also, it will be a flash ADC. Other architecture of ADCs are there: Sigma Delta, pipeline, SAR ADC. SAR ADC schematic and pipeline ADC schematic will be provided to candidates with architecture analysis, but designing a SAR ADC, whoever are knowledgeable with those ADC architectures, they know it takes a lot of time. With this 6 months, everything needs to be covered. So everything cannot be taken care. So flash ADC we can play with, tag we can play with, this all thing. And apart from this one, there is a bonus thing: the memory blocks. Memory blocks we will be teaching because memory circuits are needed in the market in nowadays. How to build a SRAM, how to build word line driver, bit cell, these all things will be taken care. But in case of ADC and PLL, ADC will be flash ADC, and PLL architecture explanation and circuit will be provided. Of course, in PLL and ADC, both it will be provided: SAR ADC and the pipeline ADC and PLL schematic. But in ADC, flash ADC will be taught.
Okay. So we will design the flash ADC in DAC as well.
Yes, that we will do it.
Okay.
That we will do it.
And which memory block you are telling? I think I'm not sure. Memory block, I don't know.
In syllabus, you can just look into the last page. The memory block options are given. What we were building it on it.
60x RAM, that is there. I think for that we need the D flip flop and all.
Yes, we need.
Simple gate, and then by using that we will make the flip
Yes,
flop.
because actually nowadays memories are also in demand. Many companies are asking for memory circuit. You recently might have came across all those other openings, so it is important part.
Okay, sir. Okay, sir. Thank you.
Okay, okay. Anyone other have any questions?
Yes, sir, like everything is covered from basics only now. Like suppose if
Yeah,
I'm
of
not,
course. See,
if,
this batch is actually for everyone. From experienced guys is also there,
yes, sir.
fresher guys is also there. If we start directly, why we are choosing an initial operational amplifier? Operational amplifier is a grassroots level circuit. Okay, I just showed you one operational amplifier just now, right? What was the
Yes.
schematic? A current mirror, a differential pair, a biasing circuit. Simple. This thing is a simple. It's a two-stage amplifier. If you are learning this one, if you are step by step, if you go, it will be easy. If you directly jump onto a big block, you will never understand things. You need the mathematics. You need to know Bodmas rule so that you can uh, so that you can solve algebra, so that you can solve Laplace transformation, calculus, Fourier series, right? So
Yes, sir.
you need this all basic things. So everything is from basics. Like if you see there, Linux basics, Linux basics, why it is needed? Every tool is running in Linux. If I don't teach Linux, then how any candidates will going to know how
And
to
sir,
do file handling and sort of things Linux?
like Cadence, we are working on Linux only, so we have to install Linux in our system, or like
No, you don't have to do
well,
anything. Tools is running in our server. You
okay,
just have to access it. Nothing
okay,
need to install in your system.
okay, sir. Okay, sir.
Because see, everyone's system is not capable, and these tools are heavy. It is not
Yes,
possible, and these are licensed tools, so we cannot do that way. So
yes, sir.
everything can be taken from the server. You can access it. The way I was seeing, it was actually from server. That way only you will use it at your end.
Okay, sir. Okay. And so whatever the tools that we are going to use, starting from basics only. Like suppose I'm not using Cadence in my college and all, so this is my first time I'm going to use Cadence. So like
That's all. The no problem. See, I told you na. From Linux basics, we will start. Linux basics means how to operate in Linux. What are PWD? What is the meaning of PWD command? What is the meaning of ls command? What is the meaning of ls space hyphen a command? These all commands and things will be taken care. Linux basics will be done. Then CMOS fabrication. Fabrication is an important thing. It's a basic thing. Any interviewer will ask you the questions. Then CMOS fundamental. What is the operating conditions? How you find GMI ID? How to find ID current? These all things we will taken care. These are the basic things. After this one, step by step, we will go to the building of small blocks. First, we will get to know how to introduce to the tool, how to operate the tool. We can build a small inverter circuit. This is the initial thing. Okay, we can simulate it, check what is the inverter output. So you make a habit, you get habituated with the tool. You understand the tool. Then we start slowly the major concepts. Then we enter the projects of operational amplifier. We implement those concepts on that one. So that this way it happens actually. Okay.
Got it, sir.
Okay. Anyone other have any questions?
Sir, in throughout the course, which PDK we will use is specific?
I mentioned 12 nanometer global foundries, 16 nanometer TSMC, 28 nanometer UMC, and 5 nanometer. 5 nanometer is a GPDK of CAD Synopsys tool. This is 5 nanometer is not a TSMC or global foundry nodes. It is a learning PDK. Only 5 nanometer I'm talking about. 5 nanometer is from Synopsys. It has to be using Synopsys custom compiler. So you get knowledge of both Cadence and Synopsys. Okay.
Okay.
But in Cadence, when you will be building, you will use real PDKs, 12 nanometer, 16 nanometer, and 28 nanometer of TSMC, Global Foundries, and UMC. Apart from this one, other technology nodes and PDKs are available, 40, 65, 180. I just shown you the operation amplifier BJ in 180 SCL. Okay, that we are actually getting taped out. We are making that chip. So these all other PDKs are also available. If anyone want to know how to work on older PDKs and higher node PDKs, they can also play with the PDK. It will be accessible for all candidates. Okay?
Okay, sir. Thank you.
Get to everyone? Any other questions? Hello. Yeah, Shauradip, I think have some question. Sir, till when will you provide the software access? Which software? The tool access you are asking, Shauradip? Once you enroll for the course, the tool access will be provided, the portal access will be provided from where you can access the tool directly. Okay?
Okay, sir. Actually, I was asking till when I mean the validity of the tool access till 6 months.
Validity is from the day of your joining, not the start of your course. Some candidates may join in the mid of the course. Actually, the tool access is counted as the candidate joined the date from that day, 7 months.
Okay.
Tool
Thank you.
access. 1 month, 6 month classroom, 6 month course, 1 month extra of the tool. So 7 month total tool access.
Okay.
Okay.
So one thing more to ask: will you provide how interview guidance like mock interview and all
Yeah,
the?
in the job assistance, what are the things I tell you?
Yeah.
Mock interview things when you are getting selected for the interview.
Yeah.
We will be help you out how to approach the interview, what kind of questions might come. If you are a fresher, what kind of questions will going to come. We will provide you the question banks. We will refer your CVs to our HR partners and the companies who have MOU with us. To them, all these things will be taken care, and at the end, certificate of completions.
Okay, sir. Thank you.
Okay. Have any other questions? If there is no questions, so you can just guys ping me. I have put my phone number here in the chat box. Okay, I have put the phone number in the chat box. You can go ping me out. We will help you out with further things. I have pinged it here. 8617262673. You can WhatsApp it here. Okay. So let's hope for the best, and we see you again in the 16th on the batch, the day the batch start. Okay, 16th May we will see you guys. Okay.
Sir, on weekends, like how many hours classes will be there?
2 hours Saturday, 2 hours Sunday. Total 100 hours of program over 6 months.
Okay, sir. And sir, timing, like at what time?
Timing we will be telling you out. It is mostly, I think, in the evening. This batch is in the evening time. 1 second, I tell you. 1 second, I tell you. This batch is in the 1 second. Hold on. I tell you, it is mostly in the evening only. 1 second, I tell you. Or morning, let me. Okay, it is an evening time batch.
Okay, sir.
It is an evening time batch. We will exactly confirm everything prior to 3 days of the batch start, evening or morning, but 95% chance it is going to happen in the evening, because morning slots are mostly not available. Okay.
Okay, sir.
Okay. Okay, then everyone, we can wind up. We'll meet again in the class. Okay. Okay. And bye, everyone. Phone number in the chat box. You can take a screenshot. You can call us back. Okay. No problem. Okay. Bye, everyone. And happy Sunday.